All right, so this is the continuation of the end of the 3B2 notes. We had talked about in class that there are two types of modeling that we were going to look at. One was the linear, y equals mx plus b. The other one was the exponential, where our formula is a equals, and then we had initial value, parentheses 1. It could be either plus or minus r, depending on which one. So I'm just writing it all in one case, and then a t. So remember, if you had a percent increase given to you or a percent decrease given to you, then you would do this plus or the minus, depending on what it was, and your percent was written in as a decimal. Now, if they give you the growth or decay factor, they're actually giving you the final answer to 1 plus r or 1 minus r. So we learned about that. We said if they just give you the growth factor, you just put that in there. You don't have to do anything with the plus. If they give you the decay factor, you just put the answer in there. Now, there's a special type of wording that we use for a couple of these growth factor and decay factors. They can use the word double, triple, or half-life. So if they give you double, it would be just a growth factor is 2. So they've already given, if they say doubling, they're telling you the growth factor is 2. If they say tripling, they're telling you the growth factor is 3. So you're just putting that in. It's already got the 1 plus r part has been done. A half-life would then be a decay factor since it's less than 1. So we would just be putting in either a half or 0.5. Okay, so let's look at an example. The number of bacteria in a Petri dish doubles every hour. So notice doubles is the growth factor. And these are the only ones that don't use the phrase, sometimes growth factor in the statement. They ask for it here. They say, what is the growth factor? It's a 2 because we're doubling. But they might just say the number of bacteria in a Petri dish doubles every hour. If you start with 10,000, how many would there be after T hours? And it's up to us to know that doubling and tripling and half-life are factors. They've already been given to us, okay? So this would be 10,000 times 2 as the growth factor to the T power. All right, so let's move on to our next slide. I've got this on preview mode, and it's kind of funny because it's making up people's names over here on the side. Don't ask me why. Okay, so here's an example we can look through together. Erase the ink. So it says melatonin is a fast acting and has a half-life of approximately 30 minutes. So half-life, that's our decay factor. We use that phrase. If you take 10 milligram tablet, write an exponential equation to model this after T time periods. Okay, so notice it is this one right here because you have the 10 milligrams that you originally took, and then it's a half-life. So that means it's a 1/2 or a 0.5 for that decay factor, and then that would be the T. Now notice that 30 minutes wasn't used because the 30 minutes was telling you how T is being represented. Like sometimes T is weeks or days or months. Here, T represents a 30-minute interval of time, okay? So it's just telling you how they're breaking up the measurement of time. All right, let's look at another one. After multiple studies, a scientist discovers a new strain of bacteria that triples every day. If a scientist started with 14 grams of bacteria, write an exponential equation to model this situation. So we're tripling. So tripling is the growth factor. So notice this is 14 grams is what we started with. 3 is the growth factor for triples, and then T is the power, okay? All right, now these we're trying to figure out based on just some data. They're just going to give us some data about our information. We want to know if the scenario is linear or exponential if they give you just back-to-back data. So what I mean by that is look at this example right here. So it says a painting sold for 1,500 and increases rapidly in value. 1 year later, it's now worth 2,550. The following year, so that'd be another year in the future, it's now worth 3,600. Complete the sentences below. That's these parts down here. Now, they're going to have drop-down menus for some of this, but let's look at this. So here's how you can tell if it's a linear, which means it has constant absolute change, or if it's exponential. So we're going to talk about these two. So if you're given just data, so year 0, it was 1,500. 1 year in the future, it was 2,550. 2 years essentially in the future, now it's worth 3,600. You can't do anything on this first line because you don't have a previous data point to compare it to. But to know if we are growing linearly, which means our dollar amount is exactly the same each time, Or is our decay or growth factor the same each time, which means we'd be exponential? Here's what you do. So you just do an absolute change to check for linear. So you do the new minus old. So the new here would be the 2,550 minus the previous, and it has to be the immediate previous one, would be minus 1,500. Notice that's $1,050. So the price increased $1,050. If you go to the next one, the new year value now is 3,600 minus the previous year, which was the 2,550. Notice this is constant. This is exactly the same increase in dollars every single year. To check if it's exponential, now you can't be both at the same time. You just do new divided by old. And if that comes out to the same decimal every single time, you know you have an exponential relationship because you're growing by the same percentage increase or decrease, okay? So look, we've got 2,550 because that's the first line where we had old data, divided by 1,500 is a growth factor of 1.7. If you do the next group, though, 3,600 divided by its previous value, the 2,550, notice that's not 1.7. It's only 1.41. So there was an increase of, because remember, the base is like 100%. So there was an increase of like 70% from year 0 to year 1, but the painting only increased 41% from year 1 to year 2. So that percentage of increase is not staying consistent. So that means it's not exponential. So note that I wrote the absolute change is consistent. So the problem can be written by a linear function. That would be your drop-down menu. Each successive term can be obtained by repeatedly. Now, when it's linear, you're either going to be adding or subtracting that same dollar amount over and over again. If they are an exponential function, the choice here would be multiplying by the same factor over and over again, because you're multiplying when you do exponential because you have that parentheses in the formula, okay? All right, so let's look at one together. So let's erase this ink. We're going to do one from scratch. Okay, used truck is purchased for $20,000 the next year. It's worth $16,000. The following year, it drops to $12,800. And then the year after that, it's $10,240. So notice I made myself a little chart. Year 0, 1 year in the future, 2 years in the future, 3 years in the future. I put down all the data they gave me. And now I'm going to check if this is linear first. And then I'll check to see if it's not linear, we'll check to see if it's exponential. If it's linear, you don't need to do this part. I will still show you that it fails if that's what happens, but you wouldn't need to go to that next step. So you always take your newest value. And again, you can't do anything in row 1 because you don't have a previous data point, minus the old one. So that's going to be negative 4,000. So it's losing $4,000 in value from year 0 to year 1. Then we would do the 12,800 minus the previous year, which was 16,000. And what you're going to notice on this is that that doesn't give me the negative 4,000. So essentially, I can stop my journey right there for linear. That gives me negative 3,200. So since those are not the same dollar amounts every single year, this is not linear. So I already know that, just I can stop at that point. You can prove it and keep going, but these have to match. And then you would have to prove that this also matches. Now we're going to check for exponential. Is it an exponential decay since it's losing value? So we do the newest value, which was the 16,000 for that year 1, divided by the previous year's value, which was 20,000. And remember, this is going to give us either a growth or decay factor, depending on if we were going up in value or down. We're going down in value, so notice this is less than 1. So technically, this means we decayed 20% from 100%, okay, because this is 0.8. So we are now doing the next year, 12,800 divided by the 1,600, because that was the and again, it has to be that previous year's value. So 12,800 divided by 16,000 is again 0.8. I need to prove it one more time just to show that pattern is maintained. So we'll do the 10,240 divided by the 1280. 10,240 divided by 12,800 is 0.8. So notice this is consistently a decay factor of 0.8. When you do new divided by old, you're finding the growth or decay factor. If it's bigger than 1, it's a growth factor. If it's less than 1, it's a decay. You're losing value. So this problem can be represented by an exponential function Each successive term can be obtained by repeatedly multiplying by, since we're doing the exponential, the 0.8. That's our decay factor. All right, let's do another one. A science student bounces a ball and records the height of the ball. After each bounce, the student records the following data. So they've got their values written here. We're going to transfer them here. So the initial one was 100 centimeters. The next bounce, we got 60. After the next bounce, it was at 36 centimeters and then 21.6. Okay, so for checking for linear, you do the new value minus the old value. We get negative 40 for that. Then we do the next new value minus the previous one for that. So 36 minus 60. And we're going to already fail the linear right here. So it's not linear. It has to be the same value all the way down when we subtract. So now we're going to check for exponential. So we take the newest value divided by the old value right before it. So that's going to give us 0.6. So again, we're decaying because we're losing height as we go out. Then we're going to do 36 divided by the previous one, which would be the 60. That's going to be 0.6. So notice that's maintaining that. So far, we're going to check one more. We need to do the 21.6 divided by the 36, just to verify. And that is 0.6. So it is going to be exponential again this time. And this one is, that also would mean always multiplying when exponential. Linear, you choose adding. And then we are multiplying by that factor, that decay factor of 0.6. Okay. All right, so I believe there's one for us to try as a, again, this is just kind of modeling the Kahoot through the class. Population of California black bears is increasing by about 30 bears per year. At the time they started tracking the population was 24,000 black bears. What is this equation? Never did they say triple, double, or half-life. They never said growth factor or decay factor. And they never said percent increase or decrease. So this cannot be exponential. This is physically every single year we get 30 new bears. That's an exact set amount. So that would be linear. Okay. And when it's linear, the slope is what you're gaining each year or losing each year. And your starting amount is, oh, and they wanted you to use T. I don't know why they did that on this one in Newton, but T would be in for our X. And then 24,000. That was how many bears we started with. So that's going to be the red triangle choice that they had here. All right, so sometimes I'll throw a linear one in there just to make sure we're paying attention. This one is going to be an exponential. Amanda planted 1,100 acres with soybeans, and she plans to increase her field size by 4% each year. Notice an increase of 4%. So that's going to be exponential. We are starting with 1,100 acres. It's going to increase. Now, this is not the growth factor. This is the percent increase. So we need to do the 1 plus that as a decimal ourselves. So that's 1.04. I just like to write the work a little bit above it and then to the T. So that's the blue choice down here, which it already ran through that for us. Okay, we just have 2 more slides. Number 16, the value of a house is increasing by 6% per year. If the home is worth 140,000 today, will be worth in 5 years. Notice this is a percent increase. That means we are dealing with an exponential model. So this would be A equals the original house price was 140,000. Then we have our 1 plus the 0.06 as a decimal. So 6% is decimal is 0.06. So it's 1.06 to the T. So there's my formula. We want to estimate the worth of the house then in 5 years. So our future value will be 140,000. Times 1.06 to the 5th. So you'll need to type this in on your calculator. If your calculator seems to give you something different than me, do the exponent part first, do 1.06, raise that to the 5th on your calculator. And then without clearing anything, times it then by the 140,000. Sometimes that helps if your calculator doesn't match mine. I'm going to round this to the nearest whole. They didn't give us directions, but let's just round it to the nearest whole. So this would be 187,350, and it's 1.5, so it'll be 52. So 187,352. Now, that is just a direct plugging in. You're plugging in for the years. Sometimes you'll get a question that has you try to figure out how many years should they have plugged in. So it says how many years until the home value exceeds 400,000. So right now we're not even at 200,000. The first whole year value that we exceed 400,000 is what we want to answer. So we can just use guess and check. We'll just pick different T's and work it out into our little equation. Remember, you just plug it in for your T, and you'll get what you get for each value. Now, I already know what 5 is. That was 187,352. So this is the value amount, the A. Okay. So we're going to maybe jump, let's just jump another 5 years in the future. Let's plug in 10. So 1.06, I'll raise that. I'm doing this offline on my calculator. Raise that to the 10th. And then I'll multiply that answer by 140,000. And I get 250,719 if I round to the whole dollar. So that's, again, not quite 400,000. And it's not even, we're barely over double now. So maybe I'll just jump another 10 years in the future instead of counting by fives, because you can jump around. If you go too far, you can back up. So I'm going to plug in 20 for my exponent. So 1.06 times raised to the power of 20, and then times that by 140,000. That's over. Okay, so now the question becomes, this is 999 if you round to the whole. The question becomes, where did we first cross that $400,000 mark? So I'm going to make a little list down here, and I'm probably going to start with maybe, this is much closer to the final answer, maybe 16. And I'm just going to work my way up until we finally cross that 400,000. So we're wanting to find the first year that they actually exceeded 400,000. Not, we don't know if that happened in year 19, 18, when did it happen? So if we plug in 16, because I just stepped back a little bit, but not quite half, and then times that by 140,000, this one's not going to be over 400. This is 355,649. So I'm just doing these calculations on my calculator. So maybe we'll go up to 17, see if we cross the 400,000. So we got 1.06 raised to the 17th, times that by 140,000. That's going to be 376,988. So again, not quite over 400,000. We'll go one more year in the future to 18, see if this does it for us. So 1.06 raised to the 18th power times 140,000. This is not it either. It's 399,607. We're not quite over 400, so it's going to probably be 19. All right, so 1.06 raised to the 19th power times the 140,000. It's 423,584. This is the first time. So it would be 19 years in the future is when they would finally have crossed the 400,000 for the first time. They were very close in year 18, but not quite over that threshold yet. Okay. So that's just using a guess and check with the formula that you got, just to see if you can figure out how long it will take. And then the last slide is, these were supposed to be on the Kahoot originally, but I made them back into slides. It says, if a series of numbers has a constant absolute change, does that show a linear model or an exponential? Constant absolute change is the exact same dollar amount, bear amount, people amount, whatever it is we're measuring. So that's a linear model. Absolute change related to linear model. If you have a growth factor or a decay factor that's constant, which is a relative change, like a percent increase or decrease, that's when you're exponential. David is a plumber who does house calls. He charges $75 for a house call and an additional $105 per hour. To find out how much he charges for a 3-hour house call would be, okay, so this is a fixed, you show up, he charges $75, and then it's a fixed rate per hour. This is your M. This is not exponential, this is linear. No matter what, every hour he stays is an additional $105. That rate does not change. It's an absolute change. Okay. It's a set dollar amount. So the model would be that he's going to charge you $105 for every hour that he's there, where X is our hours. And we're, no matter what, even if he doesn't fix anything for you, he's going to charge you $75 for coming to your house. So that's his starting fee. And then we want to charge that, we want to find that 3-hour house call. So that would be 105 times 3 plus 75. So how much would you have to pay the plumber if he worked at your house for 3 hours? That's $315 for the first part, plus add the 75 to it. You'd be paying him $390. That's for that part B part. So there's the formula. There's the fee that would be for 3 hours. Now, my next question is, if he charges you $630 total dollars, how many hours did you work? Well, that's the charge. The final bill is Y. So you can plug that in for Y. It's just a different way of thinking about it. Or you could do the trial guess and check, method, and we could solve this for X. So you'd subtract over the 75, get 555 equals 105X, divide by 105. And we would get that would be about 5.2857 ... They didn't tell us what to round to, so we'll do 1 decimal place. So this will be, he worked there for 5.3 hours. Okay. So things to note, you could have done that by a little table like I did on the last one where we did guess and check. You would have just said, what X's are you plugging in? And then you would have found, you wouldn't have gotten the exact decimal amount. Like you would have, if they told you to found the first number of hours that he exceeded this bill, you could do that. I prefer the solving method because we get the exact answer for that. And that is it. That's the end of the 3B2 notes. This is everything that finalizes what you need to be studying for the midterm. So you need to be looking over weeks 1, 2, and 3 material. We already have a review posted in the module 4 for you. I will bring copies to class next week, like I said, for our review day. But please, please, please look at that ahead of time so you know what questions you kind of already have. All right. Have a wonderful weekend.